You just heard a software-based impulse response guitar cabinet simulation running in real time on this custom digital audio processing system, featuring an STM32H7 microcontroller, audio codec, audio front ends, and control interfaces. In this video, we'll explore the basics of IR modeling and simulations, we'll see how you can get your own impulse responses or where you can download them from, and then how to implement a simple IR loader or simulator on an embedded system in firmware. We'll also do some real-world tests and measurements, for example, frequency response measurements, and then also, of course, play some guitar through this system. A huge thank you to PCBWay for sponsoring this video. I had these guitar digital audio processing boards manufactured and assembled by PCBWay using their PCB prototype service as well as their PCB assembly service. I'd strongly suggest checking out their services. They've got many more cool things such as FPC, rigid flex, as well as advanced PCBs including HDI, custom stack-ups, and much more. Make sure also to follow PCB on Instagram if you haven't already, and there they'll share many cool designs, also by customers, and occasionally, of course, also by myself as well. Again, link to the PCBWay is in the description below. Impulse response modeling and simulation and emulation of elements is very common across many disciplines and in engineering, DSP, and so forth. In this particular video, we will look at the modeling or emulation and simulation of guitar cabinets. So guitar cabinets are effectively enclosures made of a certain material, typically wood, and include one or many, up to 4 or even more speakers. These amp cabinets are connected up to an amplifier, which has a power amp and a preamp, and that then produces a typically fairly loud sound. For recording, typically people or sound engineers will place microphones at specific locations in front of these guitar cabinets, and depending on where you place the microphone and what type of microphone you use, you will get different frequency characteristics, so different sounds depending on which situation you want. So by moving, for example, the microphone, you can get a brighter, more bass-heavy, more distorted sound, and so on. This is of course quite a tedious process, requires many years of experience, and it's very loud, so doing this in, for example, an apartment is usually not possible. Therefore, in modern times, we have what's known as impulse response cab simulations or impulse response loaders, which take a model of one of these cabinets and microphones, and then we can simulate that in software and tweak parameters on the fly. And this is exactly what this video will cover. Guitar amp cabinets and modeling thereof is very practical and shows an immediately hands-on approach of why impulse responses are so useful and how to use them, and this is what we'll explore in this video. To get a model of a cabinet, we will feed in an input signal to the cabinet input, so an electrical signal, which of course has to have enough power to drive the speakers. The speakers are then driven by that signal, and we pick that up with a microphone placed where we want it to be. The question is, what kind of signal do we feed in, and how do we then process the output? Effectively, what we're doing is somewhat black box modeling, but what we're passing in as the input signal is not a guitar or not some direct audio signal, it's called an impulse or a pulse. Effectively, it's just a click. And then we measure what happens at the output. The audio waveform that appears at our microphone, again an electrical signal. I'd strongly suggest checking out the wiki page on impulse responses. Impulse responses are incredibly important in many aspects of engineering, but effectively, for a linear time invariant system, if we apply a pulse at the input and measure the output, we can completely characterize the system that's in the middle, and that's what we're doing with these guitar cabinets in this case. However, guitar cabinets and pretty much anything in the real world is non-linear, so the impulse response does not fully characterize the system for a real-world system. Depending on what power level we input, what voltage level, where we place the microphone, and so on, we of course get different impulse responses which build a non-linear system. For now, we'll assume just a single operating point, so a linear time invariant system. For a given impulse response, we get a given output response, and that's volume independent. Now, of course, you could create an impulse response yourself. You could get a power amplifier, feed that with a pulse response generated by a preamp, feed that into your guitar cabinet, place the microphone wherever you wanted to, and record the output, and then that's how you would get your impulse response. Luckily for us, however, we don't have to do that ourselves. There are many different impulse responses we can download, either for free or paid versions of people who have done this. So they will have done this for various different cabinets, they'll done this for different speaker types, different microphones, microphone placements, and so on. In this video, I'll be using the redwires.com free impulse response pack for a Marshall 1960 4x12 cabinet loaded with particular types of speakers, and they have different microphone placements as well. You just have to submit your email and then they'll send you a link to download. That's exactly what I've done, and in the archive we can see we have different impulse response results. So we have sampled at 44.1 kHz, 48, and up to 96 kHz at a 24-bit bit depth. If we open, for example, the 48 kHz 24-bit, remember this is just for a single guitar cabinet and a single speaker, we can see different subfolders, and these are different microphones they used. So an SM57 is a standard dynamic microphone. We might use a 421 or a different type of microphone. The standard for guitar is pretty much the SM57. In many cases it is. And if we open that folder, we can see all of these different impulse responses as WAV files. The prefix, so 1960 G12M25 SM57, is pretty much all the same, but what changes are the descriptions at the end. So we have cap, we have 0, 1, 2, 3 inches, and so on. We have cap edge, cone, and so on. And this refers to the placement of the microphone in front of the speaker. So we might have it placed to the cap, directly on the cap, or 1 inch away, 2 inches away, 3 inches away, and so on. So you can choose what microphone placement you want based on these impulse responses. It's interesting to listen to these impulse responses, but you actually won't hear very much. I'll play an impulse response for you just now, and what you'll hear is just a very short click. After having heard this rather unimpressive impulse response, let's see what information this impulse response contains. And the way we can do that is plot this impulse response magnitude versus time. So I'm in MATLAB now because this just lets me very easily visualize an impulse response, but you can do this in Python or any language as well. So I have one sample loaded in, an impulse response at 48K. I just picked a pretty random sample, and this is one we're going to be using throughout the rest of this video. We can load in this WAV file to an array, so just an array of floating point numbers, and as well as the sampling rate using the audio read function. And then we can just plot the magnitude versus time. And this is the result we see. So on the y-axis we have the magnitude, on the x-axis we have time. So the total length of this WAV file of this impulse response is 0.5 seconds. But most of it seems like it's actually silent. Keep in mind, this is the output, recorded at the output of the microphone, the electrical signal. The input is simply just a pulse. What we can see is that we have at the output an initial pulse, and then we have this somewhat oscillation, but this decaying transient that decays to 0. And this result here is the impulse response of our guitar cabinet. In this case, it was the SM57 microphone with the Marshall 9016 cab microphone placed at a certain position 1 inch away. And this is the sound we would then record, and this is our impulse response. Now in the time domain, it doesn't look particularly impressive. We can see there are quite a few different artifacts, let's call them, and we have a quick decay time after about 50 milliseconds, and after which nothing really happens anymore. So the majority of the information is contained up to about 20 to 40 milliseconds. This is something we should keep in mind. The time domain, again, doesn't really tell us too much. What we want to see is the frequency domain. Keep in mind, for impulse responses, if you check out, for example, the Wikipedia page, is that the impulse response contains all frequency domain information. So now let's plot the FFT, or the frequency domain response of our impulse response. The way I can do that, I wrote an FFT function which produces a single sideband FFT. I can compute the FFT, and then I'll plot frequency in hertz versus the magnitude of the FFT in decibels. Now I've plotted the FFT of the impulse response. So it's simply taken the WAV file, read out the time domain data, and computed a single-sided FFT. Remember, our sampling frequency is 48 kHz, which means our FFT ranges from 0, so DC, up to half the sampling frequency, which is our Nyquist limit, which is 24 kHz. So our frequency on the x-axis, magnitude in decibels on the y-axis. And this is the frequency response of our impulse response. And remember, the impulse response is our measurement of our guitar cabinet, the speaker, and the microphone combined into one at a particular power. What we can see is that we have a very sharp roll-off, close to 0 Hz, so we have this high-pass filter, it seems. Then we have a lot of these various peaks and troughs, some very heavy dips at certain frequencies, and an overall high-frequency roll-off, already starting at only a couple of kilohertz, and here we have 10 kilohertz. Then we have a very sharp roll-off after 15 kilohertz. We effectively just have noise. So this is the overall characterization of the frequency response of our guitar cabinet, microphone, speaker, and measurement system. The question is, now we know the frequency response, how is this useful, and how can we then use this in software to simulate the system based on our frequency response? And you might have already guessed this, but what this all boils down to, at least in this very simple case, is that the impulse response is simply the kernel or the filter response for an FIR filter, so finite impulse response filter, and I have a pretty detailed video on that on my channel, which is video number 17. So all we have to do to then simulate this impulse response, this guitar, cabinet, microphone, and speaker, is simply use the values we obtained from the time domain, pop that into an FIR filter structure, pass our input coming, for example, from a preamp, compute the FIR output, and the output is then our modeled or simulated output. That's really as simple as it is for this case. Of course, there are many different techniques you could use, but the simplest is an FIR IRR simulation. Before we continue, I'd strongly suggest checking out this video if you haven't already, or if you're unfamiliar with FIR filters, because the rest of this video will be pretty much based on this. This will also tell you about impulse responses and why we can get frequency domain information from them. It'll tell you about convolution and circular buffers and how this is then implemented in software, so please do check that out before you continue. The nice thing is then, this array is simply the time domain information which you got from our WAV file, which is simply effectively a comma separated values. So we have floating point values at every sample index, and the sample index, of course, is based on our sampling frequency, so every sample will have a different value. And these values then build our FIR filter kernel. So we can pretty much just take these values over into our software, create a FIR filter structure, and then compute the output. And that's it. That would be our impulse response loader. The problem is, and what you might have already noticed, is that this list is very, 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 very long. In essence, we saw it was about half a second for the entire impulse response. But then again, once we looked at the impulse response, we saw most of the information is contained within the first tens of milliseconds, so this entire left-hand side. Whereas after that point, we pretty much just have zeros or close to zeros. This leads us to the indication that we can probably truncate this impulse response. That is, we can effectively just take this front part, we can eyeball it and see where, okay, there's no more real information added, and that might be at 40 milliseconds, 50 milliseconds, and so on. After that, we just get zeros. The more we truncate, however, this impulse response, the less fidelity we have and the more information we lose. So for example, if we truncate already at 10 milliseconds, we still have this tail which is not included, and therefore our frequency response or our simulation won't be as accurate. The main idea behind FIR filters is convolution, and this is a fairly costly operation, and it's more costly the larger the arrays are. And this, of course, leads directly back to the impulse response. If we use a very, very long impulse response, which we have to convolve with our input signal, which forms the basis of the FIR filter, then of course this will take a lot of time, which probably won't work in a real-time system. So we will have to truncate the impulse response quite significantly to make sure this can run in real time and we don't run out of computation time. There are, of course, other methods for convolution, which are faster. For example, FFT convolution. But that is a topic for an entirely separate video. But this is a very cool way of converting to an FFT, multiplying in the frequency domain and doing IFFT, and that results in the same convolution operation, given certain boundaries, however. Again, this is a topic for another video, and we'll stick with typical convolution for this video. But again, that does mean we have to truncate this list of samples by quite a bit. You can either export the array you generated either in MATLAB and Python directly to a CSV file, and in MATLAB that would be CSV write, but I will here immediately truncate the array to just down to 256 samples, so very, very short, and save that to a CSV file. This is the plot of 256 samples of our impulse response, and as you can see, we are truncating very heavily right at the end, and there is information, of course, going to be missing, so our FFT of this will, of course, differ quite considerably to the full-length impulse response FFT, and therefore our simulation won't be as accurate. However, 256 samples is short enough that we can process this in real time. Here I've plotted the FFTs of the full impulse response and our severely truncated, so our 256 length impulse response. We can see all of the high frequency information is missing for the 256 sample truncated impulse response, but the low frequency information is pretty much there, at least the trend is, but of course these little peaks and troughs, this high fidelity information is missing. This is of course also due to the fact that we have a short FFT, so we have less bins in FFT, so that's of course another artifact, but in general this is to show that we also just lose information when we truncate. Rather than truncating just abruptly, we can of course smooth the transition at the end as well, for example with the window function, but for now, for the sake of simplicity, I've just cut off the end. We're now ready to move over to the software implementation of our IR cab simulator. From MATLAB, or however you want to do it in Python or whichever language, you can export a CSV file of your truncated impulse response. And this is what we see here, just a CSV file, or you can arrange this as column or rows, but we simply just get floating point numbers, one after the other, and we get 256 of them. And this is what we then later have to transfer over to our program. Again, we will be reusing the code of video number 17, the FIR filter video, but if you'd like to find it directly, I will leave a link to my Git page where we also have the code placed. In terms of setup of our STM32 based digital audio processing platform, please check out video number 55, which goes through detail of how to set all of that up. I do have quite an extensive DSP playlist with many different types of filters and videos, Z transforms and so on, so I'd strongly suggest checking that out if you're interested. In STM32 Cube IDE, I've imported my FIR filter header and source file. We simply have two functions, the FIR filter initialization function, which takes in coefficients, a buffer for memory, and the length of the filter. And keep in mind, our filter in this case is interchangeable with the impulse response, very simply speaking. Then we have an FIR update function, where this function takes a single input sample, does the convolution, as is the usual with FIR filters, and gives us the latest output sample. And this again is detailed in the FIR filter video. All we then have to do in our main.c file is then include the header file for the FIR filter. I'm running at a sampling rate of about 48 kHz, and this of course needs to match up at least closely to the impulse response you've chosen. So you could go with 96, 192, whatever your source is. Then I've made some defines, so for example we can change the overall gain, the amplification of this filter. I have to set this at 2 times. We need to set the length of our impulse response, and remember we exported 256, so that's what I've set here. We have a struct for the FIR, and then we have the coefficients. This coefficient array is an array of floating point variables. The length we defined previously, so 256 in this case, and these are floating point variables you would then take from the array you exported from our impulse response, which we downloaded near the start of this video. We also need a buffer, which we then pass to the FIR struct for the circular buffer. Then in int main, we do all of our setup, of course, and we simply call the FIR filter initialization function, passing all of our structs and arrays. The last thing we have to do is in our processing function, in our callback, and again, please check out the videos linked in the description to see how this is set up. We loop through the samples coming in, and then we simply set the output to be the output of the FIR filter, which has taken the impulse response samples we just exported and produces an output. And that's all there is to this IR impulse response simulation. Very, very simple. Now let's look at the test setup, upload this to a board, do some frequency response measurements, and of course play some guitar through this to see how this sounds. I'm powering the digital effects processing board via a 9-volt guitar power adapter for pedals. We're connecting up with an ST-Link V2 debugger to my host PC, and also I have connection to the input and output of my guitar processing system hooked up to the QA403 audio analyzer, with which we can then perform a few measurements such as frequency response and look at the basic performance of our IR cabinet simulator. We just saw the test setup where we've hooked up the Quantasylum QA403 audio analyzer to the inputs and outputs of the digital processing system, and I've just uploaded the firmware for our impulse response cab simulation with a length of 256 samples. We can then use the Quantasylum firmware to perform some measurements, for example frequency response, total harmonic distortion, and so on, but in this case we will focus on frequency response because this is of most interest for this type of firmware. Here we can see what impact, for example, the length of the impulse response has on the frequency response and how well the frequency response matches up with our FFT, which we took from the original impulse response kernel. I've set up the Quantasylum audio analyzer with a 96 kHz sample rate. I've set the input attenuator, and the remaining settings are setting, for example, the windowing function of the FFT, and that I would like to measure frequency response, which you can see in the bottom left. I'm using a 256K FFT with 4 averages, and generating a -4 dBV chirp signal so we can measure the frequency response like so. The frequency response of the system will be predominantly, of course, our cab sim impulse response, but then also partially artifacts due to the digital signal processing system in any case. But here we can see, very similar to what we saw in the MATLAB FFT, the frequency response of our cab simulation. We have some low frequency roll-off, we have various peaks above 0 dB gain, and then of course quite significant roll-off above about 6 to 7 kHz. On the left-hand side, I've now pulled up my computed FFT for impulse response, which we've truncated to 256 samples. On the right-hand side, we have the real measurement. Keep in mind the gain scaling is a tiny bit off, and also the frequency axes don't of course match up completely. But we can see the typical trend. So around 100, 200 Hz on the left-hand side of the FFT, we have this large, fairly wide peak in the low frequency response area, which we see on both the real response and our FFT, so simulated response, so to speak. Then all of these peaks and troughs we can also identify in the real world measurements, for example, this peak at a couple of kilohertz, and afterwards we have this drop, and we have similar characteristics between simulated or FFT'd and our measured performance. And this is for 256 length FFT and IR response. I've now reduced the impulse response length, so truncated to 128 samples, uploaded that code, and this is the updated frequency response for an impulse response of 128 samples. The QA403 settings are still the same, but as you can see, the frequency response is quite different, although we still have the overall general shape, so low frequency roll-off, fairly steep high frequency cutoff, and some ripples, very simply speaking, in the middle. But it's definitely less detailed, very simply speaking. We can change this fine into 64 length and upload the code. And now with a 64 length truncated impulse response, so quite considerably chopped from our original impulse response, we can see we lose even more detail and finesse, so to speak. Again, the overall shape is very similar. We have low frequency roll-off, some ripple, and then some high frequency cutoff, but there's far less detail. Of course, we only have 64 taps in our filter now, which therefore this frequency response is expected. But then again, keep in mind, the less taps we have, the shorter our impulse response is, the faster we can compute this. So there is, of course, a trade-off. Thank you very much for watching this video. I hope it was helpful, and I hope it showed you how you can fairly easily incorporate impulse response simulations into your own digital audio effects and processors. If you like the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any of the latest videos on hardware design, digital signal processing, and embedded systems. Thanks again for watching, and I hope to see you in the next video. Bye bye.